Hey, it's Mr. Lum again, and we are doing the January 2003 provincial exam, and we're going through by unit, and we're going to be on Unit 2 this time. So, let's get started. Here's question number 7, which is the first question for Unit 2, and it says, which of the factors below is not a condition necessary for equilibrium? Okay. So let's go through these things. So a closed system. This is very, very necessary for an equilibrium. If our system is open, that means gas or maybe products or reactants can escape, and therefore an equilibrium cannot be established. So this is a closed system is very important. As we know, temperature is very important. If we change temperature, we're going to be changing our equilibrium. So a constant temperature is very important. And equal forward and reverse reaction rates. The forward reaction rate has to equal the reverse reaction rate in order for an equilibrium to be present. So this is also very important. And finally, equal concentrations of reactants and products. No. The reactants and the products do not have to be at equal concentrations. Okay? They have to have equal rates, but they don't have to have equal concentrations. Okay, so our final answer is 7D. Let's move on to question number 8. It says here, in order for a chemical reaction to go to completion, how must entropy and enthalpy change? So, in other words, we have to memorize two rules, and that is reactions favor maximum entropy. Now, what is entropy again? Entropy is the amount of randomness in a system. Okay, so reactions want to favor the amount of randomness. They want to break into the most pieces. They want to change into the most volatile states, like they want to become gases. Okay, and so they favor the maximum amount of entropy right here. Okay, and the other thing that we have to remember is they favor minimum enthalpy. Now, what does that mean? Favoring minimum enthalpy means that they want to lose their energy. They want to go exothermic. Okay, so in a forward reaction, if a reaction is going to be going to completion, it has to have both of these things. It has to reach maximum entropy, and it has to reach minimum enthalpy. So in a reaction, from going from reactants to products, it has to go minimum enthalpy. Okay, so in other words, the enthalpy has to decrease. And the randomness, or the entropy, has to increase. And so we're given only one possible answer right here, and that is 8B. Okay? Question number 9. Here it says, consider the following equilibrium. We're given this equation, we're given a KEQ value, and it says if additional SO2 is added to the system, what happens to the equilibrium and the value of KEQ? Okay, so first off, what happens to the value of KEQ? As I tell my students, there's only one thing that is going to be changing KEQ values, and that is temperature. The temperature is not changing here. So you already know that your answer is going to be KEQ, no change. KEQ, no change. You know it's going to be one of these two, C or D. Now, if additional SO2 is added to the system, what happens. So we add SO2 into the system. It increases this concentration, and therefore it shifts. It wants to go into the forward reaction is now going to be greater than the reverse reaction, and therefore the equilibrium is going to shift to the right, and those two look pretty good to me. Okay, so our final answer for 9 is 9C. Number 10. Consider the following equilibrium system, and here we are given this equilibrium. Determine the changes in reaction rate as a catalyst is added. This is a tricky question because a lot of people want to do something like this. They're used to these graphs, where if you're given the concentration of N2, here is your concentration of N2, and they say as soon as you add a catalyst, well, the concentration remains the same. Okay, and this graph is completely correct, and it looks like that the reaction rate didn't change, but in reality the reaction rate did change, and this is what the reaction rate looks like. So now we're going to do a very similar graph, but in here we're going to go forward reaction rate, and in blue we're going to do reverse reaction rate. Okay, so our forward reaction rate is at equilibrium. Okay, we add a catalyst. What we know about catalysts is that catalysts increase the reaction rate. Okay, so we add a catalyst, it increases the reaction rate, and the reaction rate goes faster, and then it's at a new equilibrium, or not a new equilibrium, but it's it kind of levels off. But the interesting thing is that a catalyst works both for the forward reaction and it also works for the reverse reaction. So for the reverse, it's at equilibrium, so it's the exact same as here. Now, since the catalyst works for the reverse reaction just like the forward reaction, when you add the catalyst, it increases at the exact same rate. So for the whole time, since forward reaction rate and reverse reaction rate are always equal, this reaction always remains at equilibrium because forward and reaction rates are equal. But they're both increasing. Okay, they both increase when we added the catalyst. So forward reaction rate increases, and reverse reaction rate also increases. So our answer for this one, which is a little bit tricky, is 10A. So make sure to read the question, read forward reaction rate, reverse reaction rate, and your answer is 10A. Question number 11. Here it says consider the following equilibrium, and we're given this one. Which of the following is the expression? So we know that KEQ equals products. Ooh, that looks like an E. Let me try it again. Bracket products over reactants. Or in other words, KEQ equals, and then we're going to write in the products right here. So we see there's oxygen. Now there's 3 of them. So what we do, it's like it's oxygen times oxygen times oxygen, or in other words, oxygen cubed, multiplied by KCl, or potassium chloride. There's 2 of these, so we have to square this. Okay, divided by our reactants, KClO 3. Now there is 2 of these, so we need to square this. Now this is what some people are going to be writing on their thing. Okay, some people are going to be like, okay, I remember that it's here. But please look very, very closely and realize, whoa, these ones are solids right here. That's a solid, and that's a solid. Okay, and so what we have to remember is that we never put solids in our equilibrium expressions. Okay, so get rid of this, please. Okay, it's a very common mistake that people are going to be writing this for an answer. This is a solid also, get rid of this. Okay, this is the only thing that's going to have a concentration since it's a gas. So your actual answer is going to be KEQ equals oxygen cubed. Okay, so your answer should be 11A. Okay, this is probably the second most popular, most picked answer right here, but you have to realize solid, so pay attention to those subscripts. Number 12. Consider the following equilibrium. Here we're given this combustion equation right here, and it says which of the options below indicates that the reactants are favored. Okay. Well, KEQ is 0. Well, that is an interesting answer. If KEQ is 0, then that means the reaction doesn't happen. Okay. So that there is no equilibrium. The reaction didn't go forward at all. That be because products divided by reactants, products would have to be 0. KEQ is very large. So a very large number that I can think of is something like infinity. So if it's infinity, that means the reactants are 0. That means it's gone to completion. So this is something like, again, this is if it's really, really, really big number, like a number that's approaching infinity, that suggests that this reaction has gone to completion. Now, this reaction that KEQ is 0, that no reaction occurred. No reaction. Because it suggests that the products have a concentration of 0. Okay, so nothing happened. Now, KEQ is slightly less than 1. Again, KEQ is products over reactants. Okay, and if it's slightly less than 1, slightly smaller than 1, that means the reactants are larger than the products. Okay, so that means reactants are favored? Yes, reactants are favored. And KEQ is slightly greater than 1. Like say if it's like 2 or 3 or 10 or 15, that means that this number, products, is bigger than reactants, or in other words, that means products are favored. Okay, so it seems like a little bit of a difficult answer. A lot of people may want to write down something like 12A because they're thinking that, well, the reaction didn't happen, so there's all these reactants left over, and therefore the answer must be K12A. But no, the answer is 12C right here. Okay, and it is not this one. This suggests that there is no equilibrium, that there is no reaction. Okay, and we're looking for an equilibrium equation where reactants are favored. Okay, A suggests that no reaction happened. Okay, and let's work on question number 13 here. Okay, so the question says, consider the following equilibrium. We have N2O4 gas plus energy, and it forms an equilibrium with 2NO2 gas. And the question says, how are KEQ and the concentration of N2O4 affected by the addition of neon, which is an inert gas or a non or unreactive gas, into the container at constant volume? So the volume is not changing. So here, let's draw a picture of what we're seeing here. So what we have is we have some kind of container. And we have N2O4 in here. And we have some NO2 in here. And it's formed in equilibrium. Now, what it's saying is, like, we're going to add some nitrogen, or sorry, some Ne, some neon, which is an unreactive gas. And I'm just going to draw it by doing a little, maybe circles or something like that. Okay, so we add some of this stuff in here. And it says, how is this going to affect KEQ, and how is this going to affect the concentration of N2O4? Now, a lot of people want to start thinking like, well, if you add this inert gas, it's going to decrease the volume or increase the pressure. And it doesn't affect the volume. The container size, again, the container stays constant. The container did not change at all. Now, the total pressure is going to change. That is true. The total pressure is going to change. However, the pressure of the N2O4 and the pressure of NO2 is going to remain the same. In other words, the partial pressures are going to remain the same, but the total pressure is going to increase. And without getting too much into pressures, what we can say is, since this partial pressure of N2O4 remains the same, or in other words, the amount of moles per volume remains the same, that the concentration of N2O4 doesn't change at all. There's no change in it. And as we know for KEQ, the only thing that's going to be affecting KEQ is temperature. We didn't change any temperature, we didn't add energy, or didn't take away energy. So again, KEQ is going to be no change as well. Okay, so our final answer is 13A. Question number 14 now, and it says, consider the following equilibrium. We have chlorine gas, nitrogen monoxide making NOCl, and the KEQ equals 5. And it says, at equilibrium, so it's at equilibrium, the concentration of Cl2 is 1.0 molar, NO is 2.0 molar, and it says, what is the concentration of NOCl at equilibrium? So in other words, this is X. We don't know. We know that KEQ equals concentration of products over concentration of reactants. So let's write that up. So again, KEQ equals NOCl, and that's squared because there's the 2 right there. We don't write the 2 here, we write the 2 up here. So products over reactants. There's only there's no number, and there's no coefficient right here, so it's just like a 1, so we can write 1 here, or just nothing. And NO. Now there's a 2 there, so we have to write squared again right here. Let's fill in some of our numbers. So you know that KEQ is 5.0. We don't know NOCl, so you can write X, or you can just write NOCl like this. We know that's squared though. And we know that this is going to be 1.0. And that's going to be times by, now NO is 2.0. Now 2 squared, or 2 times 2, is just going to be 4.0. So I'm then going to solve for NOCl. I'm going to move this over here, and that's going to be 5 times 1 times 4 is 20. It's going to be 2 sig figs. 2 sig figs times 2 sig figs times 2 sig figs is 2 sig figs, or 20 point. And that's going to equal concentration of NOCl squared. Take the square root of both sides. Equals the concentration of NOCl. And type this into our calculator. Square root of 20, and that equals 4.47. Okay, so go back to our answers, and we see that, since it needs to be 2 sig figs, this becomes 4.5. And that's our answer, 14C. Okay, now that's the end of the multiple choice section for Unit 2, and now we're going to do the written section for Unit 2. Okay, let's start on the written section of the Unit 2 review. Here's the question. It says, consider the following reaction mechanism, and we have a 3-step reaction mechanism here. And the first question says, determine the overall reaction, and write it out here. So let's do that. So it first says, determine the overall reaction. So what we need to do is we need to get rid of all the things that are not part of our final reaction. And I like to just think of it as canceling everything out. So N2O2, it is a product here, and then it is used as a reactant on this one right here, and that'll cancel out. It's done. And same with N2O right here. Okay, now H2 and H2, these are on the same side, so they can't cancel out. They can only cancel out when they're on opposite sides of this arrow right here. So N2O2 is on a product side, N2O2 is on the reactant side here, so they can cancel out. Same with N2O is on a product side, N2O is on a reactant side, so they can cancel out. H2 are on the same side, can't cancel them out. H2O is on the same side, can't cancel them out. And we're done canceling. So we then just combine everything, just pretty much add everything up and make our overall reaction. So 2NO plus, now we have H2 and H2. We have 2 of them, so we can just write 2 H2s. And then our arrow, N2. And we have 2 H2Os, so just like before, 2 H2Os. And that's it. That's our final answer. Now it says identify a reaction intermediate. Now a reaction intermediate is something that is first found as a product and then later used as a reactant. So again, N2O2 right here is first found as a product and then later on used as a reactant. So N2O2 is a reaction intermediate. If it's first found as a reactant and then later on comes out as a product, that's a catalyst. Okay, but this one is first as a product, then a reactant, so therefore it's a reaction intermediate. So again, N2O2 is a reaction intermediate. Another one is N2O, first found as a product, then found as a reactant, and so therefore N2O. So it says identify a reaction intermediate, so you can either write this one or you can write this one, so it doesn't matter. Okay, and neither one is a catalyst. In fact, in this reaction mechanism there are no catalysts present. Okay, let's move on to the next question. And the question says, consider the following equilibrium. And we have methane, CH4 plus water. makes carbon monoxide and 3 hydrogen gas. And we see that it has KEQ values and some temperatures. So what it looks like is that someone did this reaction at 800 degrees Celsius. They calculated the KEQ, and they found that the KEQ was this number right here. And then they did the same reaction and looked and calculated the KEQ, and they found that the number was this one right here. And what we see here is at the higher temperature, the KEQ got to become a bigger number. So in other words, when you increase the temperature, KEQ became bigger. And as we know, KEQ is products over reactants. So it says, is the forward reaction in this equilibrium exothermic or endothermic? Explain your answer. So when we increase the temperature, we saw that KEQ got bigger. So what does that mean is when we increase the temperature, the concentration of the products increased and the concentration of the reactants must have decreased. So in other words, the concentration of these products increased when we increase the temperature, and the concentration of these reactants decreased. So in other words, what has happened is that it seems like this reaction shifted towards the product side, shifted to the right. Okay, so and we increase the temperature. So what that's telling me is that energy is on the reactant side. What we did was we increased the energy, and then the reaction wants to use that energy, and it shifts to the right, and therefore makes more products. Okay, and that's why we see the products going up and the reactants going down, or in other words, KEQ becoming larger. Remember, this number is much, much bigger than this number right here. So if energy is on the reactant side, well, that is pretty much the definition of a endothermic reaction. Okay, so is the forward reaction in this equilibrium exothermic or endothermic? Explain your answer. It's a endothermic reaction, and you can say because when energy is added, or in other words, heat is or temperature is added, because when energy is added, the concentration of products increases, and concentration of reactants decrease, and therefore KEQ increases. Okay, and I think that's a okay answer. Yeah. Anyways, let's move on to our final written question, question number 4. And here it is right here. It says, consider the following reaction. We have carbon monoxide and chlorine again, forms an equilibrium with COCl2, and it's asking what is the KEQ, and it says at equilibrium, this is the value of CO, Cl, and COCl2 in a 2-liter container. So this is really important. A lot of people kind of forget to read that it's in a 2-liter container. So what we need to do is we need to convert all of these things into molarities. So it's moles per 2 liters. So in other words, the molarity of this, instead of it being, is just 1.0, since it's just 2 sig figs, 1.0 molarity of CO. Cl2 right here is going to be divided by 2, so it's going to be 0.50, and this one right here is going to be 0.10 molarity. Okay, so now we can just work with these molarities. Okay, and you can write that as a calculation if you want there. But anyways, calculate the value of KEQ. So again, KEQ equals products over reactants, or in other words, it is COCl2 over chlorine times carbon monoxide. And we're going to plug in our numbers, KEQ. Now you can plug it in and do that calculation by yourself, or like 2.00 moles divided by 2 liters. I'm just going to plug in these numbers right here, which is 1.0 oops, made a little mistake, 0.10 molarity, okay, which is COCl2 right here, and divided by Cl2, which is 0.50 molarity, and carbon monoxide, which is 1.0 molarity. Okay, we then run this calculation and we find that KEQ equals, again, 2 sig figs, 2 sig figs, 2 sig figs. Our answer, this is going to be 0.10 divided by 0.50, it's 1/5 of that, so 0.20, 2 sig figs. Okay, and that's what I came up with as a KEQ value. Okay, and that is your Unit 2 review. Good luck.